So this is our experiment. My name is Jeff. These are my lab partners.
I'm Andrew. Oh, I'm Caleb.
And we did the Balmer series and Rydberg constant, which you guys have already seen. It was the first one. So the goal of this lab is to explore the quantized emission spectrum of hydrogen. These are some of the equations that we're going to use to calculate it. We have J.J. Balmer's empirical formula, which is given by that. Lambda is the wavelength of the emission line, R is the Rydberg constant, which we're going to be calculating, and then N is the principal quantum number, which is a whole number like 1 through 5 or something like that. And then we're going to use the diffraction grading equation to calculate the angle of the what's it called? The spectrum lines that we get. So like I was saying, the objective is to verify the empirical formula and to measure the Rydberg constant against the experimental values that we'll calculate. So the apparatus to complete this lab is the hydrogen lamp discharge tube, which is just a glass rod that's filled with hydrogen, and then the power supply for it. We're also going to use a diffraction grating, which has a bunch of little lines in it that are going to diffract the light waves. We're going to use a red horizontal laser and then a meter stick to measure, and then you'll need a bench, and that's basically it. So this, I guess we can use the camera to show how we set it up. This is the first activity. This is the power supply with the hydrogen tube in it. So we would just have it centered like this. You'd have your meter stick on top of your wooden holder here, and then you would shine this red laser through the diffraction grating to see where it's going to deflect the red wavelength. And we already know the red wavelength, so I guess we can switch it back now to the computer. So then we can use these equations to calculate the angle, since we already know the wavelength of the red light, and we know the distance between the interference fringes. That's what we measured, because it would break off into two. So then we can just, measure that. So that's the first activity.
So this is another picture of the setup, and it was really important for us to be in a room that we can turn the lights off so that we could clearly see where the lights were lining up on the meter stick. And to measure the values, we measured the distance of the spectral lines along the meter stick for both sides. And we also measured them from the diffraction grating to the meter stick. To calculate the angles, we found theta by calculating the arctan of distance of the spectral lines to the middle of the meter stick and distance of the grating to the hydrogen. In order to calculate the wavelengths in activity 2, we used calculated angles for spectral lines, and we used lambda equals d times sine theta, where lambda is wavelength and d is the distance between consecutive lines in the diffraction grating found in activity 1. And we also had to verify Balmer's equation, and in order to do so, we compared experimentally determined wavelengths with predictions from Balmer's formula. And in order to extract Rydberg's constant, we plotted 1 over lambda versus 1 over n squared, so we could analyze the slope to determine Rydberg's constant.
So for our data for activity 1, we first, as Jeff kind of mentioned, found like the distance between the fringe and the middle of the meter stick. That would give us the distance how the red laser was diffracted. So using that distance, you could plug that into our equation, sine theta equals lambda divided by d, where, as Jeff once again said, we know the lambda of the color red of the laser, so we're able to find sine theta. So then we're then able to use that to calculate how many lines per millimeter were in the diffraction grating. We did that with the equation 1 divided by d sine theta. So our answer, our number that we got was 9 to 17.5 lines per millimeter. And as you know, the diffraction grating is around 1,000, so we got a percent error of 8.3. Now moving on to activity 2, we found the different lines of color from the hydrogen light. So we found red, blue, purple. We again measured the distance from the diffraction grating first to the hydrogen lamp, which was 0.1 meters, and then we measured the distance from the middle of the meter stick to the different lines to just find the different distances. And using that, we could find the theta by doing arctan of the, I believe, 0.1 divided by 0.0815 for red, which is the distance from the middle. And using this angle, we can then calculate lambda for that color using d times sine theta, and then compared it to our known values to get a percent error. So then we proceeded to graph 1 divided by n, negative 1 divided by n squared, and 1 divided by lambda. The reason why we graph these is because in the equation, these are basically the different parts of the equation. So if we graph them, we were able to get the slope, which would be Rydberg's constant. So as you see, when we graphed it, we got a slope over here of 1 times 10 to the 7, which is very close to Rydberg's constant.
So the Rydberg constant influences the communication that we use every day. This constant, which characterizes the energy levels of electrons and atoms, helps us function GPS. GPS satellites emit signals that must account for gravitational time dilation, predicted by Einstein's theory of relativity. The Rydberg constant contributes to the precise calibration of atomic clocks on GPS satellites, ensuring accurate timekeeping despite the effects of both general and special relativity. As a result, the Rydberg constant helps us find accurate positioning and run navigation systems. So in conclusion, in this experiment, we were able to verify Balmer's empirical formula by measuring wavelengths of spectral lines of hydrogen and inserted the values into Balmer's formula along with the principal quantum numbers. We also measured the Rydberg constant and the observed wavelengths of hydrogen. Spectral lines were utilized to calculate the principal quantum numbers, and subsequently, the Rydberg constant was determined through linear regression analysis.